So for the last couple of videos, it's a bit of the memorization just to finish it off, and then the high levels get to do the cool stuff, which is actually work out what the voltages and products are or whether it will work or not. So we need to get this done first. So electrochemical cells are two types. There is one where it is using chemical energy to create electrical energy, and the other one's using electrical energy to create chemical reactions, chemicals. What are the similarities? Venn diagram. So they both have two electrodes. You don't have to have a salt bridge for the galvanic cell, but it will keep it clean and sometimes keep it working longer or working past more than just a short time, depending on how the setup is. They both have electrolytes, conductive medium. So one converts chemical energy to electrical, the other one electrical into chemical. The signs will be different between the anode and the cathode. Usually they just say, oh, you need a salt bridge for that, but yeah, just learn that. That's what they want you to say. And so the only thing you really got to know is convention is to put the cathode to the right-hand side, and reduction always occurs at the cathode. Everything else can be worked out. So you'll see there's a lot to be able to know. You're going to have to be able to label or explain everything. So you have to know the whole diagram. But if you know reduction occurs at the cathode, that's all you need to know. So I'm not into memorizing. I'm not into the Leo goes grr. I have a psychological break, a block in my head, and I refuse to memorize stuff because that will limit your ability to solve problems. Okay? So this is what you need to know. Now, that looks a little scary, so let's just work from the only thing we know. Okay, so we know that there's the cathode and we know there's reduction. That's all we know. Okay, so I'll put a salt bridge in there because that's what galvanic cells have, but it will still work without a salt bridge. Okay, so how much of this is memorization? How much is not? You know it's galvanic, so you know that there is electricity produced from a chemical reaction in these things, all right? And if there's reduction, well, convention is there's electrons always going this way, which is a bit of a cheat, but reduction is occurring here. So that means there is oxidation is the loss of electrons, so this must be the gain of electrons. And so electrons must be coming down, and on this side, electrons must be going off, okay? And so that's still based on reduction occurs at the cathode. Now, because this is a natural process, the electrons must be attracted to the cathode. So that's how we know this is positive, and they're repelled. And you can kind of see that they're coming off. So there's an instantaneous increase in negativity, and they're getting taken away. So at an instantaneous point, they're joining off. Now, I'm not going to go into the physics of this. So conventional current's actually opposite, and they're not actually moving. There's just like a compression wave. It's not even that. It's an instantaneous electronegative field around the wires at the speed of light. This is just chemistry, okay? So we're going to use inferior models because they're simpler and they'll get us there, okay? So we need to write chemicals that are occurring here. Now, it's normally, I don't have to do a metal, but it is normally a metal. And that will be going to a solid metal. Solid. Could be writing other things that we'll do later. And I don't have to do a non-metal. I'll just do a metal. I could do anything, but it just has to work. It just has to be to the point where you're getting electrons coming off or electrons leaving, and they don't have to be metals or non-metals. So that one, I'll call that metal, metal 2, even though that looks like something else. Should call it a different symbol. But anyway, that's done now. And so 1 molar, it's all at standard. So if we're going to use the tables later for the high levels, but we cannot worry about that for the time being. And so if that one's the anode, this one must, and we already knew that was oxidation. We've already done this here, and this is the anode. Okay, now, because there's a build-up of positive charge here and a build-up of a negative charge here, the reason we have the salt bridge is to keep it clean. Otherwise, you can get like a physical barrier produced, or one of them can layer the electrode or cathode and it won't work. So have a look at the experimental videos. Technically, I've just put one galvanic, one electrolytic video in the standard level section on the website, but you really should have a look at all of them. Really, go look at the high level ones. It'll help your understanding, and chemistry is based on experiments, so have a look at them, even if you don't have to know how to do the calculations. And so there's a buildup of electrostatic charge. Now, chlorine reacts. So potassium nitrate's a common one because they're highly unreactive. We could have potassium is even more reactive than sodium and lithium. So that's not going to cause a side reaction most likely. But because we're losing the pluses here, we're going to get a shortage of pluses. So the K pluses are going to come down, and the NO3s, there's too much plus over here. So they're balancing the electrostatic charge, the salt bridge. And so we're saying that the current travels through the ions and the electrons travel through the wires. So if you can have a look here, you can see I've pretty much done the whole thing. And all I've basically said was reduction occurs at the cathode, and I've just, like convention, I'll put it on this side. IB loves to trick you, so they'll probably swap around. There is a short... I didn't think I would see this much because this is sort of a cheat, but you do see this pop up. It basically tells you the answers. It basically tells you on the right-hand side, this one's going to here and this one's going to here. So be aware of what the shorthand notation is. You might see it. So you need to get a blank piece of paper and do what I just did. And if you check it, get a red pen and make corrections, and then grab a blank sheet of paper and do it all over again until you got this memorized, okay? Because you will get questions wrong. Standard levels, you need to know this. This will be, you just basically just be able to regurgitate, relabel things, or tell me which ones, where's electrons or what's going where. And high levels, this is just the foundation, okay? Now the last one, you have to do it for this as well. So again, I'll just go to a blank and nothing changes. Reduction occurs at the cathode. The only difference in this one is it's electrolytic. So we're forcing electrons down. They're not naturally going down, okay? And we keep it in the same beaker, and reduction occurs at the cathode. Okay, so we're forcing electrons down this time, and so it's negative because we're forcing extra charge and sucking up charge from here. So that's how you get the differences in, and this must be oxidation. Differences in what's going on here. And this one's commonly salts and stuff. So there's commonly like it doesn't have to be, and this one's in aqueous. Let's just do molten, because molten's really easy because there's nothing to compare. There's no calculations to do because you've only got one anode and one cathode. And so you standard levels have to know this now. And so the non-metal will be negative. And so of course that's attracted to the positive electrode, and this will be positive. So of course the metal, I'll just label them, and I'll call this one the salt. Well, it's both a salt. I'll just say the anion. Anion and the positive metal cation. All right, so you need to, if you see some random salt like lithium bromide or something, you have to know that the lithium's going to go over here and become a solid, and the bromide's going to go over here and become a gas. All right, that's the sort of thing you guys need to know, and that's no calculations because there's only one choice. All right, so high levels will have a lot to think about, and so what are you doing here? So electrons are coming down, and the cation's attracted to it, and then they're going to a solid metal, and then as I said over here, so the anion is getting its electrons taken away. This is oxidation, and that's often forming a gas. I'm not going to write what that is because it depends on what that is, whether it's a solid, liquid, or gas. And so for this sake here, for most of the salts, it's like it is actually a gas. So I'll just put a gas in there anyway for the time being. But think carefully about what it is, okay? And then that often comes off as actually a gas here. and that usually coats it the solid. Okay, so if they're at standard conditions, it's 1 molar, 298.15 Kelvin. And because this is forcing it through, I don't know if you know from your physics, but if you snap that in half, you can make a cross. So that's how I know that one's pos, that one's neg. And so that's how I draw this. And so that one there, the negs are pushing it out and the pluses are sucking up the electrons and the negs are thrown out. So that's how I know it's pos neg, and that's how I know which one's bigger or smaller, whatever. Okay, that's just getting far too physics now. So that would be probably inappropriate, even though high level chemistry is just physics anyway. So that's how you draw it. That's a push from a battery, at least. All right, DC, because it's got to stay in one direction. I've thrown so much physics into this chemistry thing. It's kind of funny. They've actually put DC in the syllabus. Anyway, so that's the full thing. So if you have a look, you'll see I've done it exactly correct. All right. Maybe I forgot to write aqueous. Well, I didn't write 1 molar. All right. I didn't write the standard conditions there. Okay. So do that. Look at the question carefully. I've done the sodium chloride one. Okay. So just realize it's molten, so it's not aqueous. Did I write aqueous? Ooh, I hope not. Ooh, I did. Ouch. Too used to it. You know, I'm not used to getting moltens because they're so easy. They never get asked. It's liquid, it's molten, there's no water to consider in the reaction. And there you go. Okay, so they're the correct ones. Make sure you know they've said molten and you write liqueous, it's not dissolved. Okay, again, blank piece of paper, write that out just like I said. If you get it wrong, correct it, grab a new blank paper, do it again. You've got to know those. Less than 60 seconds. I think you can write them out in 30 seconds, okay? Because you just do very quick one. So you should be able to quickly write that out in 30 seconds, all right? And do it for each and every question. Whenever you come across an electrolytic or galvanic cell question, I'll be telling you to do a lot of working out. This will probably not get a mark, so you can do it outside the box somewhere, but that'll ensure you don't stuff things up. And it takes seconds to do.